I'm super excited to welcome Ted today for our guest spotlight. Ted Xiao is currently a founding member of the technical staff at Project Prometheus. And previously, he was a staff research scientist and also a technical lead at Google DeepMind on the robotics team and also the Gemini multimodal team. His research agenda focuses on scaling physical AGI in the real world with a particular focus on approaches that can leverage internet-scale foundation models and methods that can improve with more experience. And with this, we are very excited to hear from you, Ted. Please give him a warm welcome.
Thanks for having me, Oier, and really excited to help kind of share some perspectives or showcase a lot of the progress that I've seen over the last decade or so in robot learning. And I think a lot of today will be historical, but I think a lot of it will also be directly relevant. The past tells us what the future will often hold, and the technology trends, I think, that have just only accelerated and compounded are kind of the whole reason, I would say, many times behind the entire hype and the progress happening today. To kind of set the stage for a kind of like where a lot of the really exciting work in robot learning happened, I think you can take a look back in 2015, 2016, when really awesome breakthroughs, from DeepMind like DQN or AlphaGo were happening. Those are these seminal works on the left, I think, that inspired kind of the initial bets in real world robot learning, which was still kind of a very much so unproven, crazy idea. But the essential kind of founding thesis was that we see all this immense progress in applying learning-based methods to decision-making settings, mostly in video games or board games like Go or Atari. But on the other hand, we actually did already have at that point, electromechanical systems of robots that, are still pale in comparison to what we have today. But, they were able to, have this like quite famous demo from a few decades ago at Stanford, where they were able to remote teleop this mobile manipulation robot to actually go and clean up this living room or fetch you a beer from the kitchen. The technology for this, the hardware had already existed for quite a bit now. It was just the intelligence that was the bottleneck, the generality, the actual performance, a system that could operate in many conditions completely autonomously. And so the idea was like, if the hardware is like, almost ready, or it's definitely close to there, but the intelligence is not, but then you do have these intelligence breakthroughs in these digital domains, can you kind of explore the intersection of these two? And that was kind of the founding thesis of the Google Brain team and quite a few other organizations at that time. And I think that kicked off the first era that I'll talk about today, which is the era of existence proofs, starting from around 2015, 16, 17, up until I would say about 21. And for each of these eras, I'll maybe highlight some of the works that I felt really defined kind of the vibes during this time. Some of the technical work, kind of the thought behind it, and the kind of results and the questions that were evolving during that time. Most of the work I'm talking about today is from Google DeepMind or Google Brain, just because that's where I had the most intimacy of understanding what was going on. But of course, during this time, there's tons of interesting work happening all around the world in so many different labs and different groups. But I'll touch upon some of those in the end. So circa 2016, right, DQN, AlphaGo, Google Brain just had the idea of like, what if we just bought, half a dozen, very expensive robots. Every academic lab only had maybe one. What if we just had, quite a few of them, put them in a room, had them collecting real-world experience for picking up various objects and bids. And then we just try to figure out kind of what this environment looks like, what this MVP looks like, and figure out the operations behind it. And because we're just going to be investing a ton of resources into this, let's see if we can just scale things up and get things to learn. This was, maybe you've seen some of these images, that look like the left to the middle, these arm farms where you just have a bunch of robots, a bunch of kukas together, picking up data, picking up different objects, collecting large scale data sets, mostly through some kind of autonomous exploration policy or some kind of on-policy learning. That started working a bit. There were definitely things that worked well, some things that were a bit trickier, but it worked well enough that, ambition to scale to multitask learning, a single policy that could actually understand and execute different tasks, different skills in the real world became a very strong goal. And that later then, spread beyond just a single bin to a single table to maybe a whole lab. Right, it's still a kind of structured environment, but we can mock out this kitchen-like setting you see on the right, and that was like the era of where we were really scaling up these offline data sets. And to touch upon some of the work from this era, right, we can start from this first one of like the initial first ARM farms, right, where can we even do end-to-end robot learning in the real world? Is this crazy idea something that's even possible? Here it was a lot of stuff like setting up these robots, putting them in a room, instrumenting them, making sure that the deployment, data collection, and eval would work properly, taking the kind of methods that work well, let's say in DQN, right? Q learning is pretty powerful. Learning value functions and value-based RL was really interesting, but with robotics, things got trickier with high-dimensional continuous action spaces. So how do you do that? You're not doing tabular Q learning anymore. How do you learn over a continuous value function for a continuous state and action space? What happens when your observations are now high-resolution pixels? How do you do that? One of the foundations of this work was called QT-opt, which was basically how we can apply the idea of Q learning to robotics, where we ran this, ARM farm had more than 500,000 grasps and trajectories, which was quite a bit at that time, and then training with off policy and as well as on policy online rollouts, figuring out how to do that. We also explored ways of evaluation. So this RL CycleGAN work was kind of like an OG real sim to real and real to sim evaluation protocol, where we would have a digital twin of grasping various objects in sim, and this is still the era of GANs. So style transfer to turn those sim images into realistic images, so that we could then kind of eval in a realistic looking simulation. So to the policy, whether it was evaluating in the real world or in sim, ideally it was pretty agnostic, and the sim evaluations could be a good signal. We also were looking at the full stack of not only do we treat this robotics domain as quasi-static, where you can pause anytime. The real work is dynamic. So if you want fast, reactive, dynamic-looking robot trajectories, you also need to think about how to do kind of policy execution and learning concurrently with your inference time. The next brief kind of batch of results was when we were really thinking about, okay, great, this QT-opt thing, this real-world off-policy RL seems promising. How do we scale that up? How do we get better performance? How do we get to learn many tasks? This was definitely not easy, and we were starting to hit, I would say, the bottlenecks of kind of what's challenging about these like real-world large-scale RL flywheels. And so we started exploring a variety of different methods, especially betting larger on imitation learning. With BC0, we collected quite a large teleoperated data set on this one-arm mobile manipulation robot from Google X, from Everyday Robotics, and then trained a language conditioned behavior cloning policy. We also looked at how these kinds of imitation learning methods could play well with RL, right? Get the best of both worlds. Maybe you start out with, bootstrapping from expert data, imitation learning, then you transition to this like online self-improvement, a reward function-based RL regime. How do you do that? We of course also just took the thing that kind of worked, QT-opt, and scaled it up to multiple tasks, MT-opt, multiple tasks, QT-opt. And finally, I think we'd also start exploring more novel algorithms of like how you can scale up the generality or diversity of the data distributions you're training over. Learning from play was one of these works where we just thought, okay, what if instead of collecting this very task-specific RL rollout or this expert-given trajectories of teleop, maybe you can just have experts just play around in an environment for a very, very long period of time, then use this very unstructured, ungoal-oriented data to actually extract useful, general, task-specific skills from that. And so these are all kind of, I would say, just the next batch of works that took the foundations that were established in this first era ARM farms and then scaled them up a bit more, explored different ways to apply them. And I think at the end of this section where we were, okay, these all kind of work, can we scale them one step further? A lot of folks, we had this like really big idea of like, okay, what if instead of like these incremental scaling, we just started over from scratch? We have this new robot, it's the beginning of COVID. Can we just invest now a year and a half on this really, interesting bet of building out a large contracting team, having a much larger fleet of robots, and then they're just all collecting demonstrations in the same environment, where our goal is not to solve one task or 10 tasks or 20 tasks, but hundreds or thousands of tasks. And that's what we did. We set up the operations, we scaled up this data collection effort, and to my knowledge, this is one of the largest expert demo collection kind of projects, and it was happening for over a year and a half on many robots in the environments you see here. These are now all learned policies, but going from this very wide, large-scale, diverse distribution of training into this like more open world evaluation setting was kind of a big light bulb moment for many on the team. And I think around when that data set started getting ready, when the operations started getting de-risked, that's what I would call like the beginning of the era of foundation models. Because while we were doing all this stuff, right, like the QTOP, the BC0, all of these explorations, at the same time, our neighbors and our peers in the language modeling world started to, I think a lot of the breakthroughs there really started to scale, right? This was, GPT 3.5, Instructor GPT, it was, the era of Palm, of Lambda, it was the era of Chat GPT. And so you could see when you did train on an internet scale of different tasks and data distributions on Wikipedia and Reddit, and when you did kind of treat everything as, if you can ask for it, maybe the language model has a chance of doing it, depending on prompting. All of these trends kind of were like really, really picking up steam. And so I think in the robotics world, we started to think about, it seems like this new magical alien technology of foundation models and internet scale, next level prediction seem to be really taking off. How can we leverage those models themselves, or even the ideas of these models that drive these models to create foundation models for robotics? And I'll talk about some of the highlights here. I think if you just look at what makes a foundation model work, we could break these into different components. So there's quite a certain design principles of treating everything as tokens, or there's the certain idea that like you can leverage pre-trained representations or pre-trained models entirely because the capabilities they showcase are general. Right? You can leverage foundation models as components of part of a larger system. And there's also the idea that, we went from online art farms, which were, pretty powerful with the idea of autonomous self-improvement, but in practice were very difficult because of, the fact that on-policy online data collection was very costly in terms of robot time and human kind of maintenance of managing these data distributions. If you could switch to this more offline learning setting that the rest of ML and supervised learning was kind of leading into, could we do that? So that was the bet on collecting large-scale behavioral cloning expert demonstrations, where it didn't really matter that the expert demo was not collected by your policy. The fact that it was just the golden standard Oracle behavior was quite powerful in leveraging economies of scale, so to speak. So if you combine these components, right, the design principles, the large offline robot data sets, and leveraging existing foundation models which operate mainly over language as a substrate, you get this kind of potential recipe for how you could create a robot foundation model kind of in-house or from scratch. This was Robot Transformer 1, RT1. This was what we took different performant components, a very strong vision encoder, efficient net, and with film, cross attention, token learner, transformer, backbone to kind of get to this tokens in now world, where we have RGB images, we have a language instruction, and then we generate different robot actions represented as discretized tokens. All of these design decisions, you have tokenized input outputs, you have decoder only architecture, you have an image tokenizer, and you use kind of some kind of more intelligent quantization almost or compression of action tokens. These ideas, when you put them together, that were inspired by kind of all the progress happening in broader ML, you combine them into one model. We got to this first general purpose robot transformer, which could do hundreds of tasks, using imitation learning at pretty reasonable performance, not perfect, maybe between 60s and 80s. But it was very interesting because it was like the first attempt at, just taking from first principles a lot of the kind of bleeding edge trends, scaling up to 35 million parameters, running at 3 hertz. And this was kind of like a first, I would say, existence proof and a showcase of what these kind of concepts could give you. But at the same time, right now that we had RT1, this like general backbone, we're also thinking of, great, we had to do a lot ourselves, right? We had to adapt these models, we have to rip them from pre-trained models and combine them like, Frankenstein in a lab. It also seemed that these models by themselves were extremely powerful. For example, language models, right? They were already starting to show that they would hallucinate a lot, but they would still sometimes directionally get common sense reasoning down. They would have some physical intuition. It wasn't perfect, but was there a way that we could leverage them for, robotics? One idea was that, okay, great, they can give you like a plan of like, please put an apple on a table. Great, break it down into a plan. What would you first do? What's the order of operations that you should be doing? You could send out that kind of prompt to an LLM and look at what its completions would be and look at, the kind of log probs that would give you. That's kind of what you see the numbers on the left. What's important though then is actually grounding that in what your robot policy, RT1 in this case, could actually do. And here we trained a value function, a Q function on top of RT1 that would tell you kind of like for each of these instructions in my current state, how likely is it that I could actually accomplish it? And this was a nice way then to kind of importance way or kind of combine what the language model thought was important based on their log probs with what the robot policy thought was actually doable, feasible via its kind of internal value function. And by combining these then, you could then get plans that were more grounded. Like maybe a language model would say, picking up the apple is good, but the robot policy knows that's not possible right now. I first need to navigate and go find an apple. And so by combining these two worlds, we kind of got the first collision of using language models just completely off the shelf and putting that into a combined robotic system for planning long horizon tasks, breaking them down into intermediate sub-goals that RT1 could then complete. There were other ways to use foundation models as well. One way was data augmentation. RT1, the data set that we collected, was by these days standards tiny. It was 87,000 trajectories collected over a year and a half. But the instruction diversity was actually not quite large. And so the idea was, can we use a VLM for synthetic generation to relabel kind of these episodes as different tasks that could have been feasible? Can we relabel them, create a much larger data set? And then now we can retrain RT1 on this much more rich language distribution. This is very similar to these days how models like image generation models or video models like VO are trained. A lot of synthetic captioning that kind of uses data to distill in an arbitrage what the VLM has learned, but what your data set did not contain. And then, beyond just taking LLMs for SACAN or VLMs for Guile, we also started thinking about what if instead of expressing these foundation model benefits and arbitrage via data, what if we just made them the backbone itself? And so this was kind of a project called RT2, where we explored a regime of, vision language action modeling. If you take a VLM, and which is trained on tasks like you see on the middle, like, captioning what is happening in this image or different language tasks, could you also just treat robot action prediction as a visual question answering task, given an image and given this certain kind of, what should the robot do to, close the drawer, then can you just respond in language tokens that can then get decoded to actions? And could you then scale this up the same way that VLM backbones have exhibited very powerful scaling laws? We tried this on various VLMs, PolyX and PaLM, and we mixed kind of 50-50 with internet data with robotics data on the same RT1 data set, and we found that this VLA paradigm was actually quite powerful, and you were able to transfer a lot of concepts from this internet distribution around what new objects are, around common sense reasoning, around maybe recognizing even written text, a lot of things that we wouldn't necessarily have expected because we never collected these kinds of information in our robot data set. But because they were in this internet distribution and we were always co-fine-tuning, this had a very good transfer properties when we were measuring generalization of VLAs to many new kind of out-of-distribution scenarios. Another project here was the Open Cross Embodiment project, which was I view as a seminal existence proof of whether or not you could coordinate institutions around the world, more than 30 research labs, kind of combine all the data that's been collected for various projects. Combine that data now and then see if you could learn something new from it. Could you expose it, clean that data, make it easy to kind of train on, and could you start to see then this kind of motion knowledge transferring between different robot morphologies, even though the data was collected by different people for different use cases on different robots around the world. During this time too, I would say, and I think this is one of the last ones of the era of foundation models, is now that you do have these very strong existence proofs, RT1, RT2, you have large scale data sets, and you have foundation models really maturing very fast, right? New models are dropping every week that were very smart. Could you use these better for robotics? RT2 is just kind of existence proof. If you did it this one way of just, casting robot actions to strings, essentially with some smart tricks, could this ever work? And the answer was yes, this could work. So now, I think a new interesting research area was, are there better ways to combine robotics and express them for VLMs or VLA training? Are there better ways of representing robot actions and physical motion? And there was quite a few that we explored at Google DeepMind, ranging from object-centric segmentation masks all the way to hierarchical language, where you break down a longer horizon instruction into shorter horizon substeps, looking at actual affordances, grasp angles and key points, or even trajectories, which were just from an egocentric view. But I think all of this work was happening at immense velocity from 2021 all the way maybe to 24 or early 25. I think clearly in the last year or two, there's been tremendous amounts of investments and energy and excitement into the idea that maybe these existence proofs that we saw, maybe the initial early foundation models, VLAs, this technology is actually enough to generate real value, to actually put crazy amounts of resources behind and actually go and try to commercialize. Or if you want to do more fundamental research, maybe the scale of this research needs to happen at an order of magnitude or more higher. And I think this era of scale kind of led to quite a few works up until the present day, as well as a few directions which I'll be highlighting. So the first of which is to cap off on some of the work that happened most recently at Google DeepMind. After seeing the promises of RT2, of RT1, of this kitchen mobile manipulation kind of domain, there was a huge transition on the team to, okay, these foundation models that we were using, Palm and Poly, were quite interesting, but Gemini has been in a league of its own as a very strong multimodal frontier model, right? And in addition, there was kind of this hardware trend that Aloha, this bimanual Aloha platform, where you puppeteer, was giving you much higher data throughput at much higher quality, where you can learn much more dexterous behaviors. And so this is kind of showcasing a project called Gemini Robotics, which was released around March of last year, that combined kind of this embodied reasoning, the world knowledge of Gemini 2.0, and then taught it how to do an immense amount of diverse robot actions on the Aloha embodiment that showcased a state-of-the-art in dexterity and be able to post-train to new embodiments like the optronic humanoid on the right, or this Biarm Franca setup, as well as exhibit kind of compositional generalization around reasoning at test time. This quickly followed a few months later with Gemini Robotics 1.5. Once again, it had two parts: the body reasoning part, the VLM, the reasoning part, as well as the actual VLA, the action prediction part. And here the focus was on two things. One was on thinking, so leveraging kind of language-based reasoning at test time to exhibit kind of chain of thought, as well as the second way was what was called motion transfer, which was no longer needing to post-train to adapt to specific embodiments, rather than training with all of these embodiments, the Aloha, the Biarm Franca, and the humanoid, together at pre-training time with the shared action space. This was very powerful because then a single policy, a single neural network could then control all of these robots simultaneously without any specific fine-tuning needed. But then, to then step away from the work that was being done in Alphabet at Google DeepMind, a lot of things are being scaled down. A lot of great work is happening across the industry and academia. Model generality and performance is getting scaled, robotics data is getting scaled, and I think research directions, the entropy in the research environment is also kind of unprecedented at the moment. When you look at model performance, I looked at really awesome work coming out of folks like a Pi or Generalist or Dyna. You can see learning from experience, adapting post-training has been a very increasing trend. I was very impressed by the Pi 0.6 paper that was looking at how you could really learn these longer horizon, very dexterous, precise tasks like espresso making. I think that was really cool to see. For generalization is also another type of model performance that isn't just like what's your end-to-end success rate, rather how robust are you to changing distributions. I think here, the Google DeepMind team was spending a lot of time on this and seeing very, very strong results on the ability of the Gemini robotics VLAs to generalize to all of these new situations. And now that we do have so much energy in this space, right, a lot of players that are putting out really cool foundation models on many different types of robots, just comparing how the field is advancing in terms of our knowledge and our capabilities has become a challenge, where a lot of these real world rollouts have required thousands or even tens of thousands of trials just to validate and get statistically significant samples of performance or A/B tests. So there's also really cool work happening in the scalable evaluation space, whether it's happening in SIM with the top picture, or whether it's in these decentralized distributed evals like Robo Arena on the bottom. For robot data scaling too, I think this is also one of probably the biggest buzzwords these days of there's no there's no internet of robotics data. Can we scale that? Maybe in the last era, in the era of foundation models, a lot of scaling was happening quote in-house. Right, Berkeley would collect a large data set, bridge data set, and then maybe the Google DeepMind team would collect large data sets for the one-armed mobile manipulator or for Aloha. But these days, there's a lot more embodiments, there's a lot more types of data distribution that people are targeting. How do we scale it up? And there's really big bets that are happening now. They're not necessarily mutually exclusive, but they are quite opinionated and different. You have this co-design of hardware data collect and the model out of players like Sunday Robotics or Generalist, who are really getting good at this UMI-like scale up at a global footprint, right? That you can just ship these devices off all around the world, and it's very easy for humans to put on these gloves and collect data. You also have, maybe you skip the glove entirely. You just collect hand data. You strap a GoPro or an iPhone to someone's head, and you collect, egocentric data or glasses. And this is also, I think, a huge rising trend. And finally, maybe a very important part of a data distribution to scale is the in the wild data, deployment data. And to wrap it up, I think this is my last slide. I think the science is also getting scaled. There's so many interesting scientific questions, really big bets that are being played, right? What is the importance of world models for data or evals, or even as a backbone, right? I'm really excited by world action models. A lot of the immense progress happening on Dream Zero, particularly, is a very impressive paper. Robot-free data that I mentioned, this is getting scaled up immensely, but there's so many important research questions of what are the pros and cons of this data compared to expensive, high-quality teleop data. We see a lot of thinking models with RLVR and post-training and reasoning happening in language modeling that's driving things like agentic coding. How do those ideas kind of percolate and project into robotics? And finally, I think a big elephant in the room here is all of the work I talked about today was about manipulation, dexterous general purpose manipulation, but it's clear that, for locomotion, for balance, for whole body control, there's a lot of what happens there in sim to real with RL that's seeing immense progress. Robots are dancing, they're doing kung fu, they're recovering, they're moving with very high amounts of extreme agility. And that's not happening via imitation learning. That's happening through a very other kind of learning paradigm. How do we unite what we're seeing in manipulation with what we're seeing in locomotion? With that, though, I'm happy to end here. I think if I had to just summarize this 10-year journey in a sentence, I think as a field we've made more progress than many of us would ever thought would be possible in our lifetimes. But now there's more open questions and uncertainty and open frontiers than ever. So I think the area of robotics research is both more critical and closer to fruition than ever. But there's also never been so many opposing beliefs and opinions and open research ideas where we are really entering kind of a new era of research. So with that, though, I'm happy to take any questions. Thanks.
Thanks so much for a great talk. Any questions from the audience? Okay, I see one in the back.
What do you think the role of high-quality teleoperation data will look like in the future? Will it just be absolute and fine-tuning, or do you think it will still be crucial in the foundational level of the models?
Yeah, great question. Question about the role of real-world teleop data. Is it going to be fine-tuning or elsewhere? I think again, I would say this is a huge open question, right? Of like whether or not currently, right? I would say over the last few years, real-world teleop data has been the golden standard. It is the bread and butter of most good performing policies today, where it's like because data quality has been so hard to quantify in robotics that the safe bet was just to max out data quality by doing it in-house with your own operations team or your own students who are very close to the model can also figure out whether the data is good. I think we are shifting now. I think we are now in a place where the burden of high quality data is starting to get externalized, right? To distributions that are very different from your target test time deployment. Whether or not this is going to continue, I suspect this will probably continue. I like Yuka from UT Austin has this, and NVIDIA has a data pyramid where maybe you start with internet data and sim data and maybe non-robotic video data. Then you finally, the pyramid on top, the cherry on top is the fine-tuning data. I think this is a very likely way that the world will trend. The timelines are what I'm not sure of. If this pyramid takes a decade to solidify before we really understand how to collect very suboptimal, crappy general data, but then we learn how to leverage it properly so that we only need this tiny cherry on top of real data, that would be great. We're going to get there. If it takes 10 years, though, that means that in the meantime, it's probably better to prioritize really high quality teleop data, maybe just turn that towards the distribution you want. I think there's players who are doing that, right? Who are really looking at the deployment distribution, the long tail of data as the mode. They just want to, they don't care that their method isn't scalable. They just want the best data possible on this really rare data in human homes, in a workplace, on the assembly line, in the wild, right? At the job site. So I think that's definitely for sure going to be very powerful in the next year or two. But if this pyramid of general purpose suboptimal data collection at huge diversity, if that research gets unlocked in the next year or two, then I would say the role of teleop data kind of diminishes a lot. If that research takes longer, then I think teleop is still king.
Thank you. Yeah, we have a second question.
Do you think that video action models will be the next big thing, like having the backbone learn the physics itself instead of just like putting everything on the robot data and overloading it? And do you think that, and what do you think about working in latent space instead, like the recent VJEPA like 2.1 and combining those?
Yeah, great question. Video models, world models, video world action models are these the next big thing? I think in a nutshell, yes, absolutely. I think the properties that change when you really leverage the priors that don't come from language, VLAs, VLMs, most of their capabilities come from language, from text. But then when you switch then to large-scale video-based pre-training, the priors you learn around time and space and intuitive physics are just so different and oftentimes beneficial. Things that are very hard for text-based pre-training to do, maybe video pre-training gives you for free. I'm very impressed by all the results. It's very intuitive why this makes a lot of sense. I think every year almost for the past few years, someone has tried to do this. I think now is maybe finally the time where video models, the infra, the pre-trained policies, the knowledge of like what it takes to train great video models, all of that is kind of there now, or maybe we're ready to consume this technology in robotics. That being said, though, I think the question of not whether or not this is the final thing, like will we just replace VLAs with video action models, road action models, and then we don't look back? I'm not sure, right? Or do we need something that's the best of both worlds? I say that because if you look at the existence proof in our other domains, in knowledge work, in language models, and even in like native image generation like Nano Banana, a lot of that capability is driven by text. Text is I think, extremely powerful because of the amount of priors that we get for free. You're starting from, very, high amounts of reasoning when you've kind of distilled the internet, and this really helps you kind of raise up all other modalities. So Nano Banana Pro will take a lot of time reasoning. Same with, I think, some of OpenAI's native, image media generation models. They will be actually thinking in text space, even if they're predicting in a modality that looks like pixels or audio or something like that. So if the same type of text-based reasoning that allows us to prove new math proofs actually transfers somewhat to robotics, that I think you would still need substantial amounts of exposure, I think, to text, which current video models look more like, they understand the intuitive kind of high frequency details of pixels, but VO by itself, before it's kind of fused with Gemini, is not a super smart text reasoner. So I think it really depends. I think it's absolutely on a rising trend. I think we'll see really cool progress that we've never seen before, but is this the final recipe? I'm not really sure. I still like text for many reasons, but of course I think getting the best of both worlds will be closer to the answer.
What about mobile manipulation? Do you think we're going to have some kind of like VLM conditioned on more classical computer vision stuff, like, I don't know, any kind of map of the environment, or like what is the most promising direction? What do you say?
Yeah, great question. I think, breaking this into research versus like technology, I think for research direction, when we talk about foundation models, right, I think the ethos there is not to use, let's say a SLAM mapping or different vision techniques of, especially like localization or things like that. Let's not use them as a black box at test time. Let's just distill those capabilities into the model itself, right? If there was an algorithm, a system, a software stack that could do a very specialized to do certain capabilities, let's just get the foundation model to also do it itself. That's one view. I think it's more like a purist around the science itself of like anything that humans were able to write or create as an engineered system or as a specialized, model that we train, then the generalists should be able to do that too under some kind of resourcing and compute and scale. But I think, for the commercialization, for the real world deployment,